Hello student and welcome back for DMS lecture. Previously we have seen design of centrifugal pump. In this lecture we will discuss about the design of gear pump, which is the another type of pump. Okay, this is a positive displacement pump. Okay, you can see arrangement of gear pump. A gear pump use the pair of meshing spur gears for pumping the fluid by positive displacement. Gear pumps are positive displacement pump which pumps a constant amount of fluid for which for each revolution in inlet side of the pump is separated from the outlet side. So it is axially transfer the fluid, and it is called as a mid-rate fluid transformation, or you can say a mid-rate volume could be that must be transferred by this gear. So that's why we are using in various applications. We will discuss it further. As the gear pair rotates, a suction is created on the inlet side due to which the fluid is get sucked inside the casing. The fluid is trapped between gears and casing. So the gears, you can see here, the liquid is carried. Just a minute. Okay, look at this place. So in this area the liquid is get trapped, okay, and which can be carried to the discharge side. Okay, you can see it. Okay, here it is going for discharge. You can see over here, from here to here and here to here. So in this way it is get discharged. The clearance between top land of the gears and the casing is to be very small, which is in order to 10 micrometer. The smallest clearance, along with the speed of rotation, is responsible for displacing the fluid and preventing it from the leakage backwards. Okay, these type of gear pumps having two different types. That is a external gear pump and internal gear pump. We are here looking for internal type of gear pump, sorry, external type of gear pump, because it is externally paired. When we consider internal gear pump, so gears are in line with inside the driver gear. Okay, it will be we will discuss. It is not in our uh, area, so we are only discussing this simple type of gear pump. Okay, so basic application of such type of gear pump, which is normally used for to uh, transfer liquid of petrochemicals, where the pumping of diesel, crude oil, then different type of oils, etc., which can be pumped by using such, because the quantity of the pumping volume is very important, because it have a high cost. So that's why I always said it is used for to transfer liquid or pump liquid in a metered volume. Then it can be used for chemical industry for pumping acid, plastics, mixed chemicals, resins, adhesives, etc., etc. Okay. In paint industry also, it is used for pumping the paints. In paper industry, food industry, dairy industry, and pharmaceutical industries are normally using a gear type of pump. Okay, so these are the basic application where the pump is normally used. Now let's see how we can design. Okay, so for that we will go with the problem statement. Okay, a gear pump is required to deliver 120 liter per minute of SEA 30 oil at the pressure of 25 bar. Initially what we have to do that it is given what we need to calculate, that is given. First you need to draw a sketch of gear pump, that is we can see a layout. Second, select the different type of motor, determine the power and the speed of that motor. Next, determine the module face width of the gear for gear pump, selecting the suitable material and design stresses. Check the gear for strength and wear condition. Okay. Then next one, decide the diameter of suction pipe and delivery pipes. Next, the design of shaft, and last one, the design of casing thickness, and determine the size and the number of bolts. Okay, first of all I would like to clear that the casing of the gear pump is manufactured by machining itself. Okay, it is not a casting one. No, most of the cases it is manufactured because the close clearance has to be maintained, and the material of the that gear pump is varies with the application point of view. Okay, so that's why it is very important to understand that it is not casting manufactured. So whatever the dimensions you can get, you can directly implement those dimensions for manufacturing also. Okay, so it is a special purpose type of pump because applications are very different. Rather than different, I can say where the metrated volume is to be pumped, in that location only they are using uh, this gear pump, because the fluid is also having very cost and various aspects are also to be considered. Okay, so let's see how we can design. Rated pressure, that denoted by delta P max, is 25 bar, which is nothing but 25 into 10 raised to 5 Newton per meter square. Rated discharge that is given is 120 liter per minute. That is nothing but 120 into 10 raised to minus 3 divided by 60. That is 2 into 10 raised to minus 3 meter cube per second. Medium, that is SAE 30 oil. Temperature we are considering normal condition, because temperature also get very different impact on this process. So the motor selection, as they have said, we have already done the gear pump layout assembly. Now we have to select a motor for gear pump. Now first of all we need to calculate a motor power. Motor power is equal to the given pressure, that is rated pressure, divided by overall efficiency. So the rated pressure divided by overall efficiency into actual discharge. Okay, so rated pressure is already given, actual discharge is given. Now we need to calculate the overall efficiency. Overall efficiency is nothing but it's a product of mechanical efficiency and volumetric efficiency. So mechanical efficiency, we are considering 78%, or you can go with the 75 to 80%. In that range, you can find the mechanical efficiency. About the volumetric efficiency, it is up to the 96%. If the volumetric efficiency is very less, your pumping, what you can say, your pumping quality is very less. So that's why always the volumetric efficiency, or you can say the quantity to be supplied is very less. So that's why the pumping volume, volumetric efficiency should be higher as possible as. Okay. So product of mechanical efficiency into volumetric efficiency, that is 96% multiplied by 78%. The overall efficiency to be calculated is 75%, near about. Okay, we have assumed that because, okay, uh, now putting the value of delta P max, overall efficiency, and actual discharge, what we get. The motor power is equal to 6.67 kilowatt. Okay, now we have to select standard motor, that is three-phase induction motor. You can refer PhD page number 5.124, where the different type of motors standard rating powers are given. So out of that, we have selected the nearest one, that is 7.5 kilowatt rating power. Okay, with the speed of the motor is 1500 rpm. Okay, if you want, you can add the parameters, for example, other details also. You can draw diagram also. Okay, next one, calculating for gear module. Now we are going for second phase, that is the design of gear. So initially what we done, first we have drawn the assembly diagram, or you can say layout of the gear pump. Then we have selected the motor. Okay, now third phase, that we are calling as a design of gear. Okay, and now it is a very important phase where we have to design a gear because it plays a very important role, okay, in the efficiency of our overall efficiency of the gear pump. Let consider DO is the outer diameter of gear, which is equal to mz module into number of gear tooths plus 2m, that is 2 into m. Okay, and a inner diameter of gear di is equal to mz minus 0.5 m module. Now here we are considering that the gear tooth profile is involute profile and pressure angle is 20 degree. So to avoid the interference, we need a minimum number of tooth on gear R11. Here we are considering 14. If you are considering the stub acme, a stub pressure involute profile, then 11 is fine, but we are using a normal involute profile, a 20 degree pressure angle, so we are considering z is equal to 14. You can start with the 17 also if you are using 14.5 degree pressure angle or lesser than that. So d0 is equal to m into 14 plus 2m is equal to 16m outer diameter. Inner diameter, similarly we are calculating by using the equation. So we have calculated d1 di. Now we need to calculate, we need to find out the exact dimensions. Do and di we have calculated in the form of m, that is module. So q discharge is equal to do square minus di square into pi by 4, that is the area, into width b into the speed. Okay, so put here we are considering the width is equal to 10 times of module. So breadth of the gear is the 10 times module that we have considered. So putting all the values in the form of m, we find out that qth is equal to 24,286.2 m cube. Okay, which is in meter cube per second. So m cube is the modules cube. Okay, so overall efficiency is equal to actual efficiency divided by theoretical efficiency, where actual efficiency we know that 2 into 10 raised to minus 3, that is 120 lpm. Volumetric efficiency, which is 96%. So here we are able to calculate exact value of qth. Okay, so putting the value of q actual and volumetric efficiency, we get value of qth, that is 2.083 into 10 raised to 3 meter cube per second. Now equating the equation 1 and 2, what we get, the module is equal to 4.4 mm. Okay, now selecting the standard nearest module, that is phi. So the outer diameter is equal to 80 mm, inner diameter is equal to 57.7 mm, okay, and breadth is equal to 50 mm. Now recalculating the breadth. So put referring same equation, QTH is equal to Q actual divided by volumetric efficiency. So putting all the values, what we get B is equal to 34.3, which is the actual. Now one more thing, uh, normally we are designing the gearbox or gear pump is for optimum compact area, so that's why these dimensions are very compact. Okay, so आप जब भी डिजाइन करोगे तो आपको डायमेंशन छोटे छोटे मिलेंगे, बट द कैपेसिटी विल बी सेम. ओके, तो इसके हिसाब से आपको वो प्रॉपरली डिजाइन करना है. इसमें कोई भी ओवर डिजाइन नहीं चलेगा, क्योंकि अगर इसको आप ओवर डिजाइन करते हो तो इसका डायमेंशंस यू कैन से द overall dimensions will get increase and the compactness of the gear pump will be get uh, reduced. Okay, so we need to be careful while designing the gear pump. Next one, the design of gear pair. Now the gear pair is based design based on the Lewis equation for strength. So total power required to deliver the discharge is equal to 7.5 kilowatt. That is the power rating which we have selected for motor design while motor design. So the power to be transmitted by on each gear is nothing but 7.5 divided by 2. So 3.75 kilowatt power is individually transferred by each gear. So torque torque T is equal to 2 pi and P is equal to 2 pi nt by 60. So putting all the values, we get the torque 23.87 Newton meter. Now calculating the static load on gear. Referring page number 8.4, material for a gear is C45, having design sigma B 140 Newton per meter square. Then crushing strength, for design crushing strength, sigma C is equal to 500 Newton per mm square. Now using Lewis equation, first of all find out the static load. Fs is equal to sigma B, design sigma B into Y into M. So Y is the Lewis form factor. Y is equal to 0.154 minus 0.917 divided by Z into pi. So putting all the values, that is the value of Z, minimum number of tooth. So that is the 14. So Y is equal to 0.279. So Fs is equal to 6.7 kilonewton. Now tangential load on the gear, Ft. Ft is equal to torque divided by mz by 2. So putting all the values, what you get, Ft is equal to 682 Newton. Next one, calculating the berth velocity. Here we are considering page number 8.51, and we are considering that it's commercially manufactured by using wheel cutting. So CV is equal to 6 into Vm divided by 6, which is referring page number 8.51. So to calculate Vm we can calculate pi dn by 60. So it's a peripheral velocity. So pi dn by 60. Putting all the values, what you get, Vm is equal to 5.5 meter per second. And we have considering 1500, that is a motor speed, actual motor speed. Diameter, we know that model into number of teeth on gear, so m into z, so we can get a direct diameter. So putting the value of CV Vm into CV, what do we get? CV is equal to 1.92. Now checking the static strength for dynamic condition. Okay, here condition is that the static strength, or you can say static load, should be greater than the dynamic load. So here we will check whether this condition is going to be satisfied or not. So Fd is equal to Ft into Cv. So 682 multiplied by 1.92, what we get, 1309.44 Newton, and value of Fs is equal to 6702.4 Newton. So here the static strength is greater than the dynamic strength. So our gear is safe for static condition. Now second condition, where you have to check for wear strength. For wear strength, there is a condition that the wear load is always greater than the dynamic load. So let's see, we can calculate the FD, wear load. Fw is equal to d1 into q into k into b. Okay, so d1, the diameter, that is m into z. Okay, that is 70. Q is the ratio of 2i divided by I plus 1. You can refer through the PSG. So as I is equal to 1, power transfer, you can say both gears are in the same, so transmission ratio is equal to 1. Q is equal to 1. K is equal to sigma c square sine of alpha 1 upon E1 plus 1 upon E2 into 1 upon 4. So here E1 is the Young's modulus of the material. We are using same material for both gears, so the value of E will be same for both. That is 2.1 into 10 raised to 5. Alpha is equal to 20-degree pressure angle. Sigma C, we know that the 500. So putting all the values, what we get? K is equal to 0.582. Now calculating the FW, that is wear load. So wear load is equal to 1397.38. Okay, so what we calculated, FD is equal to 1309 and the FW is equal to 1397. So here the wear load is greater than the dynamic load, so the gear is safe for wear also. Now next one, calculating the force exerted by oil on the gear, that is a F hydraulic. So horizontal component of the pressure force F hydraulics is equal to minus 1.637 P max into R into B. The negative sign indicates the water is liquid is flowing towards the left direction. So you can look at this diagram, figure number 2, where the analysis of the force analysis is given. The direction also is given. So Fy, FHY, hydraulic force is equal to minus 1.636 into 25 into 10 raised to 5 divided by 10 raised to 6 into 35 into 34.3. So hydraulic force is equal to minus 4.91 kilonewton. Now tangential radial forces which is acting on the shaft. So tangential force is equal to torque divided by PCD divided by 2. Okay, because it is acting and on the PCD. That is a radial distance which we are going to consider. So 23.87 into 10 raised to 3 divided by 70 by 2. So the tangential force Ft is equal to 682 Newton. Similarly, we can calculate the radial force. Fr is equal to Ft into tan of alpha. So 682 into tan 20 degree. Fr is equal to 248.30 or 23 Newton. Now the net force which is acting on the x direction on the shaft, Fx is equal to Ft plus hydraulic force, which is equal to 682 plus 4190.65. That is the net force on x direction acting on the shaft, Fx is equal to 4872.05 Newton. Okay, now we need to calculate a resultant force, because we know that if there is a two forces which is acting in axial x direction in y direction, so resultant force is very important and which is acting in a radial direction. So Fr is equal to Fx square plus Fy square. Putting all the values, what we get, Fr is equal to 4878.36 Newton. Now you can look at the load distribution of the shaft. Okay, So load distribution, you can get a dish diameter, where the radial load is actually acting, distances and all. Okay, dimensions we have considered. Now next, calculating the maximum bending moment of the shaft, that is a max. Assume load is uniformly distributed throughout the width of the gear, and it can be varies uniformly on the bearing also. So M max is equal to Fr by 2 into 34.3 divided by 2, that is a breadth of the gear, plus 17 by 3 minus Fr by 2 into 34.3 by 4. So putting all the values, what you get? Maximum bending stress M max is equal to 34.74 into 10 raised to 3 Newton mm. Now motor torque on the shaft, which is we have already calculated, that is a T is equal to 23.87 into 10 raised to 3 Newton per mm. Using the maximum shear stress theorem, uh, equivalent torque is equal to T square plus M max square, which is equal to pi by 16 ds cube into the tau. So tau is for material C45 is equal to 45 Newton per mm square. Now putting the value of T square, T and M max, what we get? Equivalent torque is equal to 42,150.26 Newton mm. Now putting it is equating with the equation pi by d cube into tau square. So putting all the values, what we get? Diameter of shaft is equal to 14.73 mm. Now modifying this shaft, ds is equal to 20 mm. Okay. Now if we recalculating the stresses, what we get? The design stress is greater than the induced stress. As the diameter increases, obviously the design stress, induced stress get reduced. Okay. So it can satisfy that condition. So design is safe. Now we need to select a bearing. Now bearing is a play and very important because it give a support as well as it can rotate a shaft. So for smooth operation, the bearings are very play and very important role. As a pump is connected, a pump is is compact in nature, as discussed previously also. The torque necessary to drive the gear should be minimum. So the selecting needle roller bearing because it can handle very high load with the small dimension. So we are selecting based on the diameter of the shaft, that is D is equal to 20, referring page number 4.33. The bearing number which we have selected for needle roller bearing is NA4904. Okay, so for that the equivalent load we need to calculate it, and we have to check whether what how much the life each bearing actually perform. Actually, in the sense calculated the bearing life. The equivalent bearing load P is equal to X into Fr into S, because we are considering axial load is 0. Okay, so putting all the values, that equivalent load is equal to 585.4 Newton. So there are two bearings we are using. So divide into half. So actual load on each bearing is equal to 585.4 divided by 2 Newton. That much Newton. Now the life of bearing in hours. Okay. So LH is equal to 16,666.67 divided by N into C divided by P by 2 raised to 10 by 3. Okay, it is 1 upon K. For needle bearing, roller bearing, it is 3 by 10. So it is 10. Now it is converted in that manner. So putting all the values, that is C, N and P, what we get? The life in hours is equal to 5,187 hours. Now based on the working time and working days, you can calculate the number of days also. Working time per day, you can calculate the number of days also. Now next phase, we need to design suction and delivery pipe. As it is in a compacted nature and delivering the same volume from suction to delivery, so the both suction and delivery pipe having same dimensions. So that diameter we are considering as dp. Now from net positive suction head point of view, we are considering the velocity that v is equal to 2 meter per second to avoid the bubble formation. Okay, so actual velocity discharge is equal to area into velocity. Discharge is equal to 2 into 10 raised to minus 3 is equal to 2 into pi by 4 dp square. So dp is equal to 35.7 mm. Modifying that diameter to the standard one, that is a 15-inch pipe, that is dp is equal to 36 mm. Calculating the actual velocity now. So putting all the values and calculating the actual velocity. The actual velocity is 1.97 meter per second. Okay, so that is an acceptable velocity. Now the design of casing and bolts. That is the last point of the design. Now here you can find the casing cross section of the casing, where both gears are to be apart from 70 mm. Distance between two shafts are 70 mm, which is shown over here. The radius of curve of that is R40. Thickness will need to be calculated. So design of casing is similar to the design of pressure vessel because it is similarly appearing with the equivalent diameter. D is equal to R plus D1 plus R, that is 40 plus 70 plus 40. That diameter is equal to 140 mm. So we are using dowel pins also, so that easily we can uh, assemble and disassemble with a accurate manner. So the dowel pins are normally used for properly showing the positioning purpose. Okay, so with the help of these dowel pins, you can directly insert in a proper manner, and the assembly will be very easier. Now we need to calculate the thickness. Okay, so the casting material, normally rather than casting we can say material for this casing is a C40, and the permeable strength is a sigma T into 880 Newton per mm square. Now as we are considering it is a pressure vessel, so P testing pressure is equal to 1.5 times of maximum pressure. So 1.5 into 25, that is 37.5 bar. Okay, let's see the diameter can sustain and how much the thickness we can calculate. So sigma T is equal to P testing pressure into the diameter divided by 2T. So what we get, T is equal to 3.52 mm. Now modified that thickness up to the 5 mm. Okay, so the outer radius of casing is equal to 40 plus T, that is a 45 mm now. Okay, previously it is inner diameter, that is R40, outer diameter of the casing is 45 mm. Now the diameter of casing is equal to 90 mm. Okay, now next one, the design of bolt. Okay, what is the function of bolt over here? It can be tightly fitted and reduce the leakage between the both ends, where the suction pipe and the casing is get connected, and where the casing and delivery pipe is get connected. Okay, so that junctions we need to be uh, leak proof. So calculating the bolt diameter, force acting on the bolt, that is P max into the area of cavity into the plus the test pressure into the area of gasket. So pi by 4 dO square is the area of cavity plus d1 plus dO, that is area of gasket, sorry, area of total area of cavity, that is pi by 4 do square plus d1 plus do, that is 10,624 mm square. Now, area of gasket is equal to pi by 4 casing diameter square minus outer pipe diameter square plus d1 plus 2t. Okay, so the area of gasket is equal to 2034.5 mm square. The force on bolt, putting the values what we get, the force on bolt is equal to 34.2 into 10 raised to 3 Newton. Initially we are assuming the number of bolts are equal to 8. So the force exerted on the each bolt is equal to number of bolts, force on bolt divided by number of bolts. So force exerted on single bolt is equal to 4275 Newton. Consider bolt material, that is C30, which is lower grade material than the casing, because whenever the failure occurs, those bolt can be filled, but the casing should not be filled. Okay, so that's why the lower grade material can easily replace the bolts. Okay, so the fail-safe condition can be justified. So sigma t for that material, referring PhD page number 1.4, is equal to 80 Newton per mm square. F is equal to sigma t, design sigma t into AC. Putting all the values, we can get area. Now area is equal to 53.44 mm square. Selecting M12 with the pitch 1.75, referring PhD page number 5.42 based on the calculated C value. Okay, now the area which is greater than the calculated one, so we have selected this bolt, and the area of that cross section area of the bolt is 84.3. Okay, now we need to check whether leakage occurs or not with the using M20 bolts, and the number of bolts are 4. Okay, so the casing thickness is 5 mm. Let us keep distance between a bolt center and outer surface of the casing is 25 mm by providing a flange to the casing as shown in figure number 5, which is an upper section. Okay, here the arrangement is shown. The total pitch length is equal to 2 pi do by 2 plus t plus b by 2 into 2 into d1. So putting all the values, what you get, total pitch length is equal to 579.8 mm. Now pitch circle diameter, or a pitch circular pitch is equal to pitch length divided by number of bolts. So 579.8 divided by 8. So PC pitch circular pitch is equal to 72.84 mm. Now the condition for the leak proof is circular pitch should be lesser than that of 5 times the bolt diameter. 5 times of bolt diameter. So we are putting the values. Circular pitch, that is 72.84 mm. Now 5 times of bolt diameter is M12 bolt is there. So 12 multiplied by 5, that is 60. So this condition is not satisfied. So if you are using M12 bolt with the number of quantity are 8, then definitely the leakage will be occur. Now to avoid this situation, we modified the number of bolts to the 12. Okay, now let's see. So similarly, M12 bolts are using only we are using previously we are using number of bolts are 8. Now it is increased to the 12. So let's see. So now the circular pitch is equal to 579.8 divided by 12, that is 48.32 mm. Okay. Now the circular pitch you can calculate. that is 48.32 32. Now here 5 times of the bolt diameter. Now bolt diameter is 12. 12 multiplied by 5, that is 60. So here the condition it get satisfied. So the circular pitch is lesser than the 5 times of the bolt diameter. As this condition is satisfied, the joint is a leak proof and safe. Okay, so in this manner we need to design a gear pump. Okay, I hope everyone understood some in somewhat manner. When you are practicing this problem with your own, so at that time you can be easily understood the design. So in this design the main components are, we need to design motor selection, then the gear. After the gear you need to properly select the pipe, then pipe, after that the number of bolts and the casing thickness. So these are the very important parameters which to be designed. Okay, so I'm providing the link of the design in description box so that you can download that and start the finishing the assignment. Okay, if you have any doubt you can feel free to contact me in a very any way, WhatsApp, email, okay, or message. You can do anything. Okay, I hope everybody is getting some clear about the design. Thank you. Thank you very much.